Great.
Okay. Our next speaker is Tom Rudelius from the IAS.
Great. Thanks a lot. Thanks for the to the organizers for the invitation, and thank you for putting together this nice workshop, even in these strange times. So indeed, today I'll be talking about generalized global symmetries and the swampland, based on 4 papers, which should be appearing in this year. One with Shuheng Xiao, hopefully later this week or next, and then a couple of papers with this large group, and another paper with these 2 collaborators. So, quick outline, I'm going to very quickly review the swampland. I'm then going to introduce the notion of higher form global symmetries, and we'll then put these 2 together in 3 different ways, looking at implications for the completeness hypothesis, looking at these things called Chern-Weil global symmetries, which is something that I will define in this talk, approximate global symmetries, and then we'll end with some conclusions. So a lot of us here are interested in the swampland. There have been many swampland conjectures which have been proposed in the last 15 years or so. These are conjectures which are things that are conjectured to be true of all theories in the landscape. So for instance, theories in the landscape are not supposed to have any exact global symmetries. There are many of these conjectures. Some of them have more evidence in their favor than others. Some of them have more interesting implications than others. And as we all know, unfortunately, there tends to be sort of this trade-off where the most interesting conjectures tend to have less evidence in their favor. There are also relationships between these various conjectures. And Irene had a slide very much like this a few moments ago. Things like electromagnetic duality, Kaluza-Klein reduction can be used to relate these various conjectures to one another. The goal for my talk today is to introduce some new links into this web of swampland conjectures. And so in particular, I'm going to argue that the statement of no global symmetries and suitable generalizations thereof can be used to motivate a large number of other conjectures, and also maybe even tie into some other interesting questions about regarding phenomenology, things like even the existence of axions and the QCD axion equality problem. So to begin, let's introduce or perhaps review the notion of higher form global symmetries. A Q-form global symmetry in a quantum field theory is a global symmetry in which the charged operators are supported on Q-dimensional manifolds. So the case of an ordinary global symmetry that we know and love from QFT1 would correspond to the case of Q equals 0. Here, the charged operators are just local operators supported on points. Global symmetry transformations form a group G, which may be either discrete or continuous. Ordinary global symmetries with Q equals 0 may be either non-abelian or abelian, but for Q greater than 0, they're necessarily abelian. When G is continuous, then under some reasonable assumptions, there is a conserved D minus Q minus 1 form, another current J, which is closed. Some of you may be more accustomed to calling this a Q plus 1 form current. So for instance, you might be used to saying that if you have an ordinary global symmetry, you have a 1 form another current. If you prefer that convention, then everywhere you see a J in my talk, you should replace it with a star J, the Hodge dual of J. But in this talk, I'm going to follow the convention of Gaiuto, Kapustin, Seiberg, and Willett in their original paper on this topic. And we're going to call this a D minus Q minus 1 form. In the modern view of global symmetries, symmetries are generated by these operators, what are known either as symmetry generators, charge operators, or in some contexts, as Gukhov-Witten operators. These operators are associated with an element of the group G, and they're supported on manifolds of dimension D minus Q minus 1. They satisfy a fusion law. So if I take 2 of these operators living on the same manifold M with different elements of the group G and G prime, I can fuse them to get a third operator living on the same manifold labeled by an element of the group G double prime, where G double prime is related to G and G prime simply by group multiplication. So the fusion law here is inherited from the group multiplication law. Crucially, these operators are topological. And this is really the hallmark of a global symmetry, the existence of these topological operators which fuse according to group multiplication. By topological here, I mean that if I consider some physical observable, some correlation function that involves one of these operators, and I deform the manifold M prime in a continuous way, it won't affect any of these physical observables, provided that in this deformation process, I don't cross over any other operators. For the case of a continuous symmetry, say U1, we can be a little bit more precise about what these operators are. Namely, this operator is given simply by the integral, the exponentiated integral of the Noether current over the manifold M, where here this alpha labels the elements of the group. Symmetries are associated with word identities. And in this language, a word identity says that if I consider some charged operator, which carries charge under the global symmetry, and I surround it by some symmetry generator, I can shrink this symmetry generator and at the expense of picking up a phase. So this is equal simply to the charged operator I started with times a phase depending on the element of the group G as well as the charge of the operator V. Pictorially, it looks like this. I take my charged operator, I surround it by one of these symmetry generators. Because the symmetry generator is topological, I can shrink it at will. And if I shrink it all the way to a point, I'm going to get this charged operator times a phase. Sort of the prototypical example of a higher form global symmetry comes in just ordinary Maxwell theory. So I have a U1 gauge theory with no matter and no magnetic monopoles. This theory will have actually two one-form symmetries, a U1 electric one-form symmetry and a U1 magnetic one-form symmetry. Their Noether currents are up to these constant factors, simply star F and F respectively. And the conservation of these Noether currents follows simply from Maxwell's equations. D star F and dF both vanish in the absence of any electrically charged particles or magnetic monopoles. These are one-form symmetries, so that their charged operators are supported on manifolds of dimension 1. They're nothing but the Wilson lines and the 't Hooft lines, respectively. Pictorially, concentrating from here on out on the electric one-form symmetry, I can take a Wilson line, surround it by one of these symmetry generators, which is given more explicitly by the integral of the Noether current. This is equal to the Wilson line I started with times this phase, which again depends on both alpha, the element of the group, and Q, the charge of the Wilson line. These symmetries can be broken. The way to break the electric one-form symmetry is to introduce charged matter into the theory. So let's suppose that we add in some fermion into our theory of mass M and charge N. You can immediately see that this is going to break the electric one-form symmetry because star F will no longer be conserved in the presence of this fermion. D of star F is no longer equal to 0. Another way to see that this U1 has been broken is to note that in the presence of this fermion, the charge N Wilson line can end. So this Wilson line can now end on a local excitation of the fermion. And this means that we can try to compute this correlation function here in two different ways. So we're going to consider the correlation functions we've been considering that show up in the word identities. We have a Wilson line. We have a symmetry generator which surrounds the Wilson line. But now the Wilson line can end in the presence of this charge N fermion. So what that means is that we can shrink this symmetry generator to a point. And as we saw, this is going to give us back the Wilson line we started with times this phase, e to the I alpha n, where here n is the charge of the Wilson line that can end. But on the other hand, we could also compute this correlation function in a different way. Namely, because we're assuming that this operator is topological, we can slide it down here with impunity. And once we have this operator down here, we can shrink it to 0 size, and that's just going to give us a trivial phase. So we see that computing this correlation function two different ways, we either get just the Wilson line itself, or we get the Wilson line times this phase. So for these two things to be equal, this is telling us that the phase has got to be equal to 1. In other words, e to the I alpha has got to be an nth root of unity. What this means is that in the presence of this fermion, the full set of operators that we started with, the full set of U1 charge operators that we started with, are no longer topological. The only ones that remain topological are the ones that satisfy this condition, and these are precisely the ones that furnish a Zn one-form global symmetry. So we see that the existence of the charge n fermion has broken the U1 electric global symmetry down to Zn. Now, one last point in review. So far, we've been talking about quantum field theories. But you might ask, what happens to these global symmetries in quantum gravity? In a very old lore, one of the first so-called Swampland conjectures that was ever written down, you might say, is the statement that there are no global symmetries in quantum gravity. The original argument from Misner and Wheeler, reviewed by Banks and Seiberg, dealt with the case of continuous global symmetries, continuous zero-form global symmetries. But more recently, this 2018 paper of Harlow and Oguri has argued that, at least in the context of ADS-CFT, you can make a more general statement. And so the claim of Harlow and Oguri is that in the context of ADS-CFT, one can show that there cannot exist any p-form global symmetries for p less than d minus 2. So this is a more general statement, and the general tagline is that you're not supposed to have higher form global symmetries, at least of sufficiently low dimension, in quantum gravity. So this is one standard lore. Now let's talk about another standard lore, which is the completeness hypothesis. Again, this is another example of a swampland conjecture that predates the term swampland. It goes back to Polchinski in 2004. And the statement of the completeness hypothesis is that whenever you have some gauge theory, some G gauge theory in D dimensions, coupled to quantum gravity, then you must have states in every representation of the gauge group G. So this is what's known as the completeness hypothesis. And there's a third lore, actually, which is that the first two lores I just mentioned are related. Namely, the completeness hypothesis, the existence of states in every representation of the gauge group, is supposed to be related to the absence of global symmetries. And there's a reason why this third lore exists, which is that in some cases, it's true. And we can see this simply from what we've already discussed regarding U1 gauge theory. If we have pure U1 gauge theory, we saw that we get a U1 electric one-form symmetry. If we have states of charge n, this is broken down to a Zn subgroup. And that means that if you have states of every charge, then there's no electric one-form global symmetry at all. And so you can see that there's this one-to-one correspondence. Precisely when you satisfy the completeness hypothesis and you have states of every charge is exactly when the global symmetry disappears. So demanding that these one-form global symmetries should be absent implies completeness. Now, unfortunately, this third lore is not always true. For a non-abelian discrete gauge theory, like for instance S3, you do not have, in general, a one-form global symmetry, even if you don't have any charged matter. So even if the spectrum is incomplete, there's still no one-form global symmetry. So this presents a counterexample to the naive third lore, which I just mentioned. However, it turns out that there is a more general statement which is true here. In pure S3 gauge theory, it's true that there are no one-form global symmetries. However, there do exist more general topological codimension 2 operators. Remember, the hallmark of a one-form global symmetry is the existence of topological codimension 2 operators which fuse according to group multiplication. For these more general topological operators that exist in S3 gauge theory, we still have these topological codimension 2 operators, but they satisfy a more general fusion algebra. Namely, if I fuse two surfaces, I don't just get a single surface on the right-hand side over here, but I, in general, get a sum over topological surfaces. And so one can show that, in fact, the correct statement is the completeness of S3 gauge theory is equivalent to the absence of topological codimension 2 operators, what are sometimes referred to as Gukov-Witten operators. This is a specific example of a more general statement. So the standard lore, completeness of spectrum, is in one-to-one correspondence with the absence of a one-form electric global symmetry, is true when G is a compact connected Lie group, like U1 or SUN, or a finite abelian group, like Zn. But more generally, for G a compact disconnected Lie group, like O2, or a finite non-abelian group, like S3, completeness of spectrum is in one-to-one correspondence with the absence of Gukov-Witten operators. In other words, topological codimension 2 electric operators. So the standard lore was wrong, but this revision is correct. There's a way to revise it so that the standard lore is now correct. And this is interesting because it raises a very natural conjecture. If you believe that global symmetries should not be allowed in quantum gravity, and the hallmark of a global symmetry is the existence of these topological operators, then it's very natural to conjecture that, in fact, quantum gravity shouldn't have any topological operators of sufficiently small codimension. It's actually interesting, if you try to generalize the Harlow-Oguri argument to this case, you actually run into some difficulties. And this will be explained more in a paper to appear very shortly with Shuheng Xiao. So at the moment, it's actually not clear that this conjecture is true. It remains an open problem, but I think it's a very natural thing to conjecture, and it's something that is worth looking into further. So thus far, we've seen that if we generalize the statement of no global symmetries to a more general statement of no topological operators whatsoever, we have this very close connection with the completeness hypothesis. Let's now move on to a completely different direction, which is what I'm going to call Chern-Weil global symmetries. If you have some G gauge theory in quantum field theory, such a gauge theory is going to give you conserved currents of the form J equals trace of F wedge F wedge F wedge F, some number K times. In this talk, we'll be primarily focused on the case of K equals 2, but these sort of currents are going to exist for more general K. And the conservation of these currents, the fact that D of J is equal to 0, follows in the abelian case simply from dF equals 0 in the absence of any magnetic monopoles, or for a non-abelian example, it follows from the Bianchi identity. So these conservation laws are fairly general. They don't require too many particulars of the theory, and as a result, they're not very easy to break. As I say, we're going to be primarily focused today on the case of K equals 2. This is going to be a 4 form, so in general, it's going to generate a D minus 5 form global symmetry. In 5 or more dimensions, this is a perfectly reasonable thing to talk about. But in 4 dimensions, this is sort of a degenerate case, because trace of F squared is a 4 form, and so it's trivially conserved in 4 dimensions. Nonetheless, although this is not quite precise, there is a sense in which it does generate a -1 form global symmetry, as it has quantized integral periods. Sorry, something got cut off here. It has quantized integral periods, and the conserved charge associated with these is instanton charge. So there's a sense in which this makes sense as a conserved current in 4 dimensions, but really, if we want to be more precise, you should be thinking for most of this talk in 5 or more dimensions. So these are just global symmetries that exist in quantum field theory. But we know, or at least we tend to believe, that in quantum gravity, these symmetries should not exist. And so from the perspective of quantum gravity, you have 2 ways to deal with these sorts of Chern-Weih global symmetries. Either they must be broken or they must be gauged. So to gauge such a symmetry, what one does is couple the conserved current to a gauge field, which in this case is a D-4 form gauge field. So for the abelian case here, what this means is we're going to add in a coupling of the form C D-4 wedge F, and the result is that the equations of motion will tell us that F wedge F is then equal to D of something. In other words, the current is not only closed, but exact. And having exact current is really the hallmark of having a gauge symmetry. So that's one thing we can do. We can gauge the symmetry by coupling it to a D-4 form. Another option is to break the symmetry. So for the case of an abelian gauge field, the way to do this is to add monopoles. As a result, df is no longer equal to 0, so d of f wedge f is not equal to 0, and the symmetry is broken. In the non-abelian case, the way to break these Chern-Weih global symmetries is by unification. So let's suppose that we are working in d dimensions. Again, think d greater than or equal to 5, most likely. And let's consider just ordinary gut symmetry breaking. So we have SU5 broken to SU3 times SU2 times U1. In the ultraviolet, if you're looking at this, you will expect just a single Chern-Weih current, trace of F SU5 squared, which you expect will be gauged by some D-4 form, as we just saw. If you were an IR effective field theorist, though, you would look at this theory and you naively think that you should have 3 Chern-Weih currents, one for each of the gauge groups. That means that as an IR theorist, you actually would overcount the number of Chern-Weih global symmetries, and thus perhaps overcount the number of D-4 forms that you expect to exist. Because what happens as you go to the ultraviolet and you complete this SU3 times SU2 times U1 is that 2 of the Chern-Weih currents will be broken. So those symmetries will be broken. We'll only have one symmetry in the UV, which needs to be gauged in order to remove it. This is interesting when it comes to the existence of axions. So axions, as we are familiar with, are ubiquitous in string compactifications. They show up all over the place. From the perspective of these Chern-Weih currents, we can start to see why that might be. Anytime we have a Chern-Weih current, either we break it, presumably by some sort of unification, or we gauge it. But if you start in d greater than 4 dimensions and you gauge such a Chern-Weih current with a D-4 form, then upon compactification to 4 dimensions, this is going to reduce to an axion, which couples by the usual coupling of an axion to the gauge field strength. And so this helps us see why axions might be so prevalent in quantum gravity. We aren't simply looking under the lamppost, but rather axions play a crucial role in that they're needed to remove would-be global symmetries by gauging them. One last point that I'll mention regarding axion physics is the implication here of the Chern-Weih perspective for the so-called axion quality problem. A common concern in solving the CP problem is what's known as this axion quality problem. And the concern is that you might have misaligned contributions to the axion potential, which could spoil the solution. So here we have this contribution from the QCD axion. It has a minimum at the appropriate value of theta. But if you add in some other contribution, say from some other axions with a phase delta, then if delta is not equal to 0, then these two will be out of phase. And if the dominant contribution to the potential comes from this term, then it would spoil the solution to the CP problem because it would put the minimum elsewhere. So you worry that you might have a case where S other, these other instantons, are smaller than SQCD. The Chern-Weih perspective doesn't completely get rid of this worry, but it helps it somewhat. Because given 2 types of instantons, we either expect, A, that we'll have 2 different axions which couple to them in which case both Chern-based symmetries are gauged by these axions, or else we expect that we need one of the symmetries to be broken, so that one type of instantons can sort of transform into the other. What this means is that it suggests that we only need to worry about gauge sectors that can be unified with QCD. The ones that cannot be unified with QCD will have a different Chern-Bay current which needs to be gauged. The ones that are broken are going to unify with QCD into some larger gauge group. And this means that the same sort of dynamics that give rise to the QCD axion potential might also be explaining the other contributions to the potential. And so these two contributions, which maybe naively seem independent, are not going to be independent when we account for this fact that breaking the Chern-Bay global symmetry requires unification. Again, this is a little bit of a degenerate case because we're dealing here with the case of the -1 form global symmetry. But to the extent that a -1 form global symmetry makes sense, we expect that this sort of unification will occur here as well. So we've seen then that the absence of these Chern-Bay global symmetries in quantum gravity may actually have some interesting implications for axion physics. Finally, let me talk a little bit about approximate global symmetries. Approximate global symmetries are a little bit harder to define than an exact global symmetry. But from what we've said so far, we can sort of give a moral definition of what an approximate symmetry is. You remember that when you have an exact symmetry, we get these exactly topological charge operators. When we have an approximate global symmetry, therefore, we expect charge operators that are almost topological, in the sense that they have only slight sensitivity to variations in the manifold M on which they're supported. Another way to say this is that the current for these symmetries should be almost conserved. D of j is equal to some parametrically small number. A Swampland proposal that I want to set forth and then try to justify is that not only should quantum gravity break global symmetries, but it should also badly break them within the context of effective field theory. In other words, you shouldn't have any approximate global symmetries at the Planck scale. All symmetries should be badly broken by the Planck scale. So why should this be true? Well, the original arguments against exact global symmetries in quantum gravity from Misner and Wheeler dealt with the issue of exactly stable problematic black hole remnants. And the idea is, if you think that exactly stable black hole remnants should be illegal, then you might also think that long-lived black hole resonances should also be illegal, which would also tell you that not only should you not have exact global symmetries, but you shouldn't have approximate global symmetries at the Planck scale either. The statement that global symmetry should be badly broken at the Planck scale matches our intuition in simple cases. For instance, if we have a complex scalar field, it has a U1 rotational symmetry, which is broken by higher dimension operators of this form. In quantum gravity, we expect that these sort of operators will be suppressed by the Planck scale. And suppressing these operators by the Planck scale is precisely what you need in order to ensure that the symmetry is no longer approximate at the Planck scale. But finally, another reason why you might think that approximate global symmetry should be badly broken at the Planck scale is the fact that this seems to agree with a number of Swampland conjectures that we already tend to believe. I'll speak today just on one, which is the weak gravity conjecture, which holds that in a d-dimensional U1 gauge theory, you need to have a super extremal particle. That is, a particle whose charge to mass ratio is greater than or equal to that of an extremal black hole, roughly equal to 1 in Planck units. Pictorially, the weak gravity conjecture says that you need one particle which lies on or below this line in this space of charge versus mass. And this was connected to the notion of higher form symmetry breaking. You remember we started with this Lagrangian with Maxwell theory. We added in a charge n fermion like this. And we saw that this broke the U1 electric global symmetry down to a Zn subgroup, as can be seen from looking at the equations of motion. From here, it's interesting to consider two different limits. The first one is the case where you take the gauge coupling to 0. In the limit as g goes to 0, the dynamics of the fermion and the gauge field completely decouple. And so you effectively get back the one form U1 electric global symmetry in this limit, as you can see from the fact that d of star f goes to 0 as g goes to 0. Another limit to consider is the limit as m goes to infinity. Here you can integrate out the fermion, and at long distances, any symmetry breaking effects of it become exponentially suppressed. So in either the g goes to 0 limit or the m goes to infinity limit, the U1 electric one-form global symmetry is restored. And these are precisely the limits that the weak gravity conjecture is trying to forbid. The weak gravity conjecture says that you need either the charge to be sufficiently large or the mass to be sufficiently small. You can't take g to 0 or m to infinity with the other one held fixed. We can make this intuition more precise, as you can see in our forthcoming paper or in my talk from the 2019 Swampland workshop in Madrid. One can do this computation a bit more precisely with a more precise definition of an approximate global symmetry. And what you'll ultimately find is up to an order 1 factor, exactly the weak gravity bound. The charge of the fermion has to be greater than m Planck, than m over m Planck up to some order 1 factor. This is for the case of a single fermion. If you instead consider a theory with many light species, what you'll find is that not just a single particle has to satisfy this bound, but in some sense, the average particle satisfies the weak gravity bound. And this is very reminiscent of some versions of the weak gravity conjecture, namely the tower and sublattice versions, which tell you that you should have not just a single particle which satisfies this bound, but a whole tower of them. For lack of time, I'll move on here, but suffice it to say that by similar arguments, one can connect the absence of approximate global symmetries not only to the weak gravity conjecture and the tower and sublattice weak gravity conjecture, but to a number of other swampland conjectures as well. So let me conclude. The main takeaway from my talk, the main thing to remember today, is that by slightly modifying the statement of no global symmetries in several different directions, we can connect this statement to a number of other swampland proposals. To begin, we generalized from no global symmetries to no topological operators. This led us to a connection with completeness of spectrum. Next, we looked at a particular class of global symmetries known as Chern-Weig global symmetries, and we saw that these had implications for axion physics. Finally, we talked about approximate global symmetries and saw that their absence could be related to these other swampland conjectures. The main punchline is that the statement of no global symmetries seems to be incredibly powerful in terms of the swampland program, with implications for many different facets of the swampland program. Some open questions. It would be nice to prove a no topological operators conjecture and to develop and prove a more precise statement of the no approximate global symmetries conjecture. It would be nice to extend it from continuous to discrete global symmetries. Conceptually, this is easy. Practically, the computations become harder in this case. It would be nice to tie this into other swampland conjectures and perhaps to other areas in phenomenology. Thank you.
Thank you very much, Tom. So our first question will be from Federico.
Hi, very nice talk. So if we go back to the example in which you discussed the one-form electric symmetry in just QED, you said that if we have fermions with all possible charges, then the symmetry is broken completely. My question is, would it be enough to have just two fermions with coprime charges?
Sorry, could you say that again? Which slide?
So there was a slide in which you said that if we assume completeness hypothesis in just QED, the one-form electric global symmetry is broken completely. I'm asking, can you just have two fermions with coprime charges and break completely this symmetry?
Yes, that works, yes.
Because then I would think maybe I mean, you don't need full completeness to break this this global symmetry.
So if you have two fermions with coprime charges, then you can build a state which is possibly a multi-particle state of charge 1. So completeness is not saying that you need to have necessarily fundamental particles of any given charge. It's saying that you need some sort of states, which could be multi-particle of every charge.
Okay, thanks.
Next question is from, oh, sorry, are you done, Frederick?
Yeah, you said you are studying gauge theory of S3 group. So I have a similar question. So do you really need all the S3 representations, or you can have a subset and still break completely the global symmetry?
Yeah, it's the same sort of thing. You could have particles in two different representations, such that a multi-particle state, if you consider the tensor product, you get some other representation showing up. You don't necessarily need to have a single particle state of every representation.
Okay, thank you.
Mm-hmm.
Next question from Helix and Bernardo. Okay, maybe we'll come back to you. Kumran next.
Yes, thank you. That was a nice talk, Tom. I have a question about the conjecture you have about the no topological operator. Have you thought whether or not that can be related to the no covordism conjecture? It sounds similar.
That is a good question. I haven't thought about it. I guess my understanding is that, so from your paper with Jake about cobordism, the argument that you made as to why such things should not be allowed is that they lead to higher form global symmetries. So what I guess I don't see at the moment is how to relate such cobordisms to more general topological operators rather than simply symmetry operators, which fuse according to a group structure. So maybe you might have better ideas about that, but I don't immediately see necessarily how to connect them.
Well, the naive picture is that topological operators are things which are deformation invariant, and in that context, it fits with that cobordism triviality that there's nothing to measure in some sense. But then, yeah, it sounds similar in a way.
You're right. It sounds similar. I'll have to think more about it.
Okay, Bernardo.
Sorry. Now you listen. Yeah. Okay. So I have a question about the general conjecture of no global symmetry. So most of the examples you gave were about continuous global symmetries. Is this conjecture to be true even in the discrete case? Even if it's, sorry, not continuous, compact case. So you gave examples about compact symmetries. So my question is about non-compact symmetries. Is the conjecture supposed to be valid even in the non-compact case?
So I'd say it's supposed to be true, yes. First of all, there are other arguments that have been given that all gauge groups in quantum gravity should be compact. But as far as global symmetries, the compactness of global symmetries, so the argument of Misner and Wheeler dealing with black hole remnants would indeed could indeed be generalized to forbid non-compact, continuous, ordinary global symmetries. The argument of Harlow and Oguri, which is, again, specifically in the context of ADS CFT, and also relies on some other assumptions, specifically what they refer to as splittability. Under those assumptions, their argument also would apply to the case of a non-compact global symmetry, as well as a discrete one, or etc. All that that argument really requires is the existence of these topological symmetry operators. So that argument could be used quite generally. It doesn't, as I say, it doesn't actually, at least immediately, carry over to the case of more general topological operators that are not symmetry generators. And so there some more work is needed, but for the case of a non-compact symmetry, their argument should go through.
Okay, we're tight on time, but one quick question from Isabel and quick answer from Tom.
Okay, yeah, so my question is just related to the fact. So you've been discussing this U1 gate symmetry, and you've put as an example like this fermion that carries charge n. But of course, when you minimally couple a U1 gate theory to gravity, you already have black hole solutions carrying all charges, both electric and magnetic charges. And I would have thought that that's sort of like trivially doesn't allow for any global CN to be left over. So I'm just wondering whether you thought about, once you take into account the fact that there are also charged black hole solutions, how that weakens some of the implications of what you've discussed.
Yes, it does weaken the implications, which is really the motivation for considering the third section of the talk, which is, can we make a stronger statement, not only that global symmetries don't exist, because as you say, those can be broken very weakly by black holes, but actually, can we make a stronger statement about how badly symmetries need to be broken? And that has led us, I think, to more interesting connections with some of these conjectures.
Okay, thanks.
All right, let's thank Tom again.